We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will introduce rotational motion. In particular, we will introduce the angular kinematic variables that are used to describe this motion and will relate them to our usual one-dimensional kinematic variables. We will also define the moment of inertia, the parameter in rotational motion that is analogous to the mass in translational motion. We will evaluate the moment of inertia for a collection of discrete particles as well as for symmetric solid objects. Until now, our studies of dynamics have been restricted to linear motion of objects described in a Cartesian coordinate system, x, y, and z. In our recent discussions of systems of particles, though, we have discovered that the motion can be described as having two components. One, the motion of the center of mass, and two, the motion relative to the center of mass. As an illustration of the motion relative to the center of mass, we will look at the rotation of an object about an axis through the center of mass. Our first step is to develop a coordinate system in which these rotations can be described naturally. Here we see a disk rotating about an axis through its center. The orientation of the disk at any time can be described by a single parameter, the angle theta through which the disk has rotated relative to its initial orientation. We call this angle the angular displacement. The time rate of change of the angular displacement, d theta dt, is called the angular velocity, omega, and the time rate of change of the angular velocity is called the angular acceleration, alpha. These equations look strikingly similar to those we have used to describe one-dimensional kinematics. The reason for this similarity is simply that this rotational motion can be described by a single angular displacement theta, just as linear motion can be described by a single spatial displacement x. If we now consider the special case of a constant angular acceleration alpha, we can derive the equations for omega and theta for this motion by integrating the defining equations. The resulting equations for omega and theta are absolutely identical in form to those describing one-dimensional motion at constant acceleration, with the substitutions alpha for a, omega for v, and theta for x. We can now make another useful connection between rotation and one-dimensional kinematics by obtaining the relationships between the angular and linear kinematic parameters used to describe the motion of a point that is a fixed distance r from the rotational axis. In the case of one-dimensional motion along the x-axis, we needed to specify which direction we choose to be positive so that the signs of displacement and velocity and acceleration have meaning. In exactly the same way, we need to specify which direction of rotation we choose to be positive so that the signs of angular displacement and angular velocity and angular acceleration have meaning. Although we are always free to choose either direction of rotation to be positive, it is customary to pick the counterclockwise as the positive direction. With this choice, the angular displacement theta agrees with that usually used in trigonometry. Since all points on the disk are rotating together, we can determine the linear displacement, speed, and acceleration of any point on the disk in terms of the corresponding angular parameters. For example, when the disk turns through an angular displacement theta, a point located a distance r from the rotation axis will move through a distance s along a circular path of radius r. This distance s is determined from geometry to be just equal to the product of the radius and the angular displacement as measured in radians. Taking the derivative of this linear distance with respect to time, we find a simple relationship between the speed of the point and the angular velocity of the disk. Taking the derivative of this linear speed with respect to time, we find a simple relationship between the tangential acceleration of the point along its circular path and the angular acceleration of the disk. We will now expand our discussion of rotations by considering the motion of a rigid object made up of a set of point particles connected by massless rods as shown. This object rotates about the fixed axis with a constant angular velocity omega. We'll assume we know the masses of each particle, m sub I, and also the distances of each particle from the axis of rotation, r sub I. The total kinetic energy of this object is defined to be the sum of the kinetic energies of each of its parts. We found in the last slide that the speed of a rotating object relative to the axis of rotation is just the product of its angular velocity and its distance from the axis. Therefore, we can rewrite the expression for the total kinetic energy of the object in terms of the angular velocity. Since this angular velocity is a constant, we can take it and the common factor of 1/2 outside the sum. We will define the remaining sum, namely the sum of the product of each mass with the square of its distance from the axis, to be the moment of inertia of the object about this axis, and will denote it with the symbol I. Note that the resulting expression for the kinetic energy of this object has the same form as the kinetic energy of a point particle. We have just replaced the velocity by the angular velocity and the mass by the moment of inertia. In other words, in the same way that the mass of an object tells us how its kinetic energy is related to the square of its velocity, the moment of inertia of a rotating object tells us how its kinetic energy is related to the square of its angular velocity. In a sense, the moment of inertia plays the same role in rotational motion that the mass plays in the simpler motions we have studied up to this point. As we learn more about rotations, we will see this conceptual connection between mass and the moment of inertia appear again and again. We will spend the remainder of this pre-lecture exploring the properties of the moment of inertia in more detail. The most obvious difference between mass and the moment of inertia is that the moment of inertia depends not just on the total mass, but also on exactly where that mass is located. Indeed, the moment of inertia even depends on your choice of the rotational axis, since we are measuring all distances relative to this axis. To see how this works, let's do a simple example. Here we see an object made up of 4 point particles of equal mass m arranged in a square of side 2L centered on the origin. The x and y axis are as shown, and the z-axis points out of the screen. We will first calculate the moment of inertia of this object if it is rotated about the x-axis. Since the distance of each mass from the x-axis is just equal to L, the sum we need to make to determine the moment of inertia is simple. Here we see that the moment of inertia for rotations around the y-axis is the same as it is for rotations about the x-axis. What about rotations about the z-axis? The distance of each particle from the z-axis is clearly larger than L. Indeed, using the Pythagorean theorem, we see that the square of the distance to each mass is twice as big as before. Therefore, the moment of inertia for rotations about the z-axis is twice as big as the moment of inertia for rotations about the x or y-axes. We've seen from this example exactly how to calculate the moment of inertia of an object made up of discrete point particles about any axis. We've learned that the moment of inertia does depend on the choice of the rotation axis. On the next slide, we will generalize this calculation to the case of a continuous solid object rather than a small collection of points. Here we see a thin rod of mass m and length L centered along the x-axis. How do we go about calculating its moment of inertia for rotations about the z-axis? Well, as you might guess, we will need to replace the discrete sum we used on the last slide with an appropriate integral. We'll call the mass per unit length of the rod lambda. Now each infinitesimal piece of the rod has a length dx and a mass equal to the product of this length and the mass per unit length. The contribution to the moment of inertia from such an infinitesimal piece of the rod located a distance x from the origin is just equal to the product of its mass and the square of its distance from the axis, x squared. To find the total moment of inertia, we integrate over the length of the rod. The mass density can be taken outside the integral, and we are left with the integral of x squared, which is just x cubed over 3. Evaluating this expression between the limits, we obtain the expression shown. We can replace the mass density by the total mass divided by the length of the rod to obtain an expression that is proportional to the product of the total mass and the square of the length of the rod as expected. We know the moment of inertia depends on the choice of the axis. Suppose we want to calculate the moment of inertia about an axis that is parallel to the z-axis, but passes through the end of the rod rather than its middle. How does the calculation change? Well, we can just do the integral again, this time shifting the location of the rod to the right so that its left end is at the origin. Evaluating the integral, we see that the moment of inertia about the end of the rod is 4 times as big as the moment of inertia about its center. This result is reasonable, since more of the mass is further from the axis when it is located at the end of the rod rather than at its center. We will now do another example, that of a solid cylinder, that will illustrate some general features of moments of inertia of solid objects. Here we see a solid cylinder of mass m and radius r. The axis of the cylinder coincides with the z-axis, and its end surfaces are located at z equals 0 and z equals L as shown. Since this object has cylindrical symmetry, our integral will be simplified if we use cylindrical coordinates, namely r, phi, and z, rather than Cartesian coordinates. Here we see the volume element illustrated as dr times dz times r d phi. To integrate over the mass of the cylinder, we use the mass element dm, which is just equal to this volume element, times rho, the mass per unit volume of the cylinder. To evaluate the moment of inertia about the axis of symmetry, the z-axis, we just need to integrate r squared dm over the entire cylinder. Here we see the resulting three-dimensional integral. The z and phi integrals are trivial, just being equal to 2 pi L. We are left then with just the integral of r cubed. Evaluating this integral and simplifying, we see that the moment of inertia of the cylinder about its axis is just equal to 1/2 mr squared. Note that this result does not depend explicitly on the length of the cylinder, only on its mass and radius. For example, if we were to cut the cylinder in half through a plane perpendicular to the z-axis, we would have 2 cylinders, each with half the mass of the original cylinder. Therefore, the moment of inertia of each new cylinder is just half of the moment of inertia of the original cylinder. Consequently, we see that if a system is made of 2 or more parts, and we know the moment of inertia of each part about some axis, then the total moment of inertia about that axis is just the sum of the moments of inertia of the parts. This result may seem somewhat trivial, but it will prove useful later. On the last slide, we determined that the moment of inertia of a solid cylinder about its axis was proportional to the product of its mass and the square of its radius. We can determine the moment of inertia of any other object with cylindrical or spherical symmetry in exactly the same way. We will always find this same result, that the moment of inertia will be proportional to the product of its mass and the square of its radius. The constant of proportionality will be different, of course, for each different shape. The larger this constant, the more mass is located far from the axis. For example, It is easy to see that for a cylindrical shell, this constant of proportionality is just equal to 1, since all of the mass is located at the radius of the shell. Here we see a solid sphere and a solid cylinder. We expect the constant of proportionality for the sphere to be smaller than that for the cylinder, since more of its mass is concentrated near the axis. When we do the calculation, we see that this constant for the sphere is 2/5, which is indeed smaller than the factor of 1/2 we have calculated for the solid cylinder. Similarly, we expect that the constant for a spherical shell is smaller than that for a cylindrical shell. We conclude with a brief discussion of the main points of this prelecture. First, we introduce the angular displacement theta, the angular velocity omega, and the angular acceleration alpha that are used to describe rotational motion. We developed the kinematic equations that describe motion at constant angular acceleration and found they were identical in form to those that describe translational motion at constant linear acceleration. We determined that the displacement, velocity, and acceleration of any point that is rotating is simply related to the corresponding angular parameter. Second, we defined the moment of inertia about an axis for both discrete and continuous mass distributions. We determined that the kinetic energy of a system of particles in rotational motion is equal to 1/2 the product of the square of the angular velocity and the moment of inertia about the axis of rotation. Finally, we determined that the moment of inertia for any cylindrical or spherical object can be expressed as the product of a numerical factor and the product of the square of the radius and the total mass of the object. This numerical factor reflects the distribution of the mass. The larger the factor, the further the mass is concentrated from the axis of rotation.